Hello everyone, it's me, Mr. Younger. I'm here to give you an example using the law of Biot-Savart, which is probably the most complicated looking formula that you'll run into in any of the calculus-based physics courses, like physics for scientists and engineers or university physics. It's a pretty complicated formula, but it does have the advantage of being correct for calculating the actual magnetic field that we've experienced experimentally. So I've made it in my sort of own form, not unlike I do with my electric field equation for Coulomb's law for the electric field. And now I'm going to apply it to an infinitely long straight wire so that you can understand how to apply it in general. Let me begin by sharing my iPad screen. So you can see I actually have the iPad screen shown here. I actually drawn the wire, which is the blue, two blue lines on each side of the y-axis. And in actuality, I think I'm going to make that y-axis the z-axis, uh, just so I can make an argument about specifically what the direction of the electric or of the magnetic field is. So I'm going to change that axis to the z-axis. And if this is the case, if I were to leave x there, for instance, the y-axis would have to point into the page and the z-axis would be up. And you'll see where that comes in relevant in a second. So let me start off by writing out solution, which is, as always, what I write, where I write what I'm going to use and what information I've been given of that sort. What we have in the law of Biot-Savart is that there's a differential bit of magnetic field d sub dB that is equal to mu 0 I over 4 pi times GL cross RP minus RDL divided by the magnitude of RP minus RDL raised to the third power. Now, this is a 1 over r squared sort of law, but in order for us to put a vector direction that would give the actual correct direction for the magnetic field, I had to use the vector RP minus RDL. If I'd used that as a unit vector, then it would have had a r square or the distance squared in the denominator. But because I used the full vector, we had to divide by another magnitude to make it equal to uh, the equivalent of basically a unit vector. Otherwise, I would have increased the actual magnitude of the magnetic field by a magnitude of RP minus RDL. The DL, by the way, is a differential line segment that is parallel to the wire and points in the direction that the current is traveling, and that's conventional current, the direction that we pretend positive flows, positive charges go. The RP is a vector that points from the coordinate origin of whatever coordinate system you use to the point P at which we wish to know the magnetic field. RDL is a vector that points from the coordinate origin, again, of whatever coordinate system you use, to the DL. So I'm going to one by one point out what all those are and then work out the actual integral. So for starters, we need to create a DL. And as I said, the DL is supposed to be a differential vector that is parallel to the wire and points in the same direction as conventional current flow. So I am going to use my green pencil to actually make a DL. So this will be the head of my DL vector, and this will be the tail of my DL vector. And in fact, the length right here will be the length, technically, since it's along the z-axis. I'm going to call that length dz. So in other words, this measure from here to here is dz, and therefore we can call dl the specific vector, dz k hat because its length is dz and it points in the positive z direction, which is the k hat unit vector. You could also use the z hat unit vector, of course. We'll also use the idea, which appears obvious here, that this distance from here to here is actually consistently going to be z, whether I'm up on the vertical half of the z coordinate, the z axis, or the lower half of the z axis. So the distance from the origin to the dz, which is the dl vector, is just the coordinate z. So that means I can go ahead and write rdl, which I'll write right here. rdl has a length equal to z, but it points in the positive z direction, which is the k hat direction. So I'm going to call it rz k hat. And for this one, I'm going to use a purple vector just so it can stand out a little better. So this is our RDL vector. And I'll label that. That's the RDL vector. Now I also need the RDV vector, or excuse me, the RP vector. And the RP vector is supposed to point from the origin to the point at which we wish to know the electric or the magnetic field. So I'm going to draw again using a purple vector, a vector from the origin to the point P at which we wish to know the magnetic field. And I think you can see from that 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 vector has a length r and points in the positive x direction. So we're going to call it r, and we're going to say it points in the I hat direction. So that really is the vectors that we need to compute this. Of course, we also need to find the difference, the RP minus RDL, and that's pretty straightforward. I'll go ahead and write that now. So RP minus RDL is actually equal to R I hat minus Z K hat. And you can actually notice exactly what that vector is. I'm going to do so by drawing the vector in red. And I'm going to try to use the tool for this application where it makes my vectors look like perfect straight lines. And yeah, that seemed to work pretty well. That last line wasn't too good, but I'll draw the head on again without the tool. So this vector, the red one, is RP minus RDL. And I think you can see from that that the magnitude of RP minus RDL is actually quite straightforward. Magnitude, actually, let me write it in green again. So the magnitude of RP minus RDL, we notice that the two components of it are, of course, perpendicular. One's z and one's r, so that should be the square root of r squared plus z squared. And now we have all the bits and pieces. Now I will have to calculate a cross product, and I will do that as well. So let me start with that one. I'm going to go ahead and compute a cross product of dl cross rp minus rdl. At this point, we're actually starting to fill in the formula. So I might, in fact, I'm going to go ahead and start using the blue marker. So with the blue marker, I will write in dl cross RP minus RDL. And that's going to be, of course, DL, which is DZK hat. And that's going to have a cross product taken between it and RP minus RDL, which is R I hat minus Z K hat. Now, you might think we could put this all in a matrix, and you're perfectly welcome to do that, but it turns out there's a lot easier way. You can just use the distributive property and then use the linearity of the cross product, which basically says that when you take the cross product of, let's say, a scalar times a vector plus another scalar times another vector, then what happens is taking the cross product is the equivalent of pulling the first scalar out in front and then taking the cross product of the vector with the vector that was left, plus pulling the second scalar out in front of this other vector and then taking another vector with it. So in fact, the linearity of it could be seen something like this. If I had A cross, let's say C vector plus D vector is the equivalent of C times A cross C plus D times A cross D. So that's the linearity property. We can use that, as you can see. I'm going to go ahead and erase it just so we'll have that room. And we're going to use that linearity property along with the basic idea of what is the cross product of I hat with J hat, I hat with K hat, J hat with K hat, and then the other orders as well. So when I do that, we get equals DZ and R are the constants on the first cross product. So I'm going to put R DZ and then I'm going to write K hat cross I hat. I'll put that in parentheses. And now I'm going to let the DZK hat hit the second term. There's already a minus out here, and I'm going to write the Z from the second term, the second product or the second factor times DZ, and then it's K hat cross K hat. So another property of dot products is that, for instance, let me write it over here, A cross B, the magnitude is equal to the magnitude of A times the magnitude of B times the sine of the angle between them, and that really should be that formula should be given with a formula as well as an actual diagram, and this is the diagram that should accompany such a equation, where it's basically showing that if you put the vectors A and B tail to tail, theta is the small angle between them. And because of that, you can see that, for instance, K hat cross I hat is going to be 1 times the sine of 90 degrees. But then we also have to choose a direction. And K hat cross K hat is going to be 1 times the sine of 0 degrees, which is going to be 0. So we don't even have to worry about the direction on that one. So I'm just going to go ahead and write that K hat cross K hat is 1 times the sine of 0 degrees, which is 0. And I can use K hat cross I hat, and this is 1 times the sine of 90 degrees, but it also spits out a vector. So we got to figure out what that vector is. Now, if you draw a right-handed coordinate system, you can easily check using your right-hand rule what K hat cross I hat is. So let me draw a little coordinate system over here. This one's going to be Z. And since we drew it with the X to the right in this one, I'm going to draw it the same way here so that the Y actually goes into the page. So there's our Y. And then the X is to the right. And of course, this means that I hat is this direction. J hat is this direction. And K hat is this direction. Now, when you're trying to take a cross product, for instance, K hat cross I hat, you let your index finger be K hat, and you let your middle finger be I hat, and you hold it like this with your right hand. And then you make sure your your index finger and your middle finger are at 90 degrees, because these two are actually separated by 90 degrees. And then you make sure your thumb is pointing up at 90 degrees to both of those. And with that right hand, you say, here's the k hat direction, which is straight up. Here's the I hat direction, which is straight to the right. And then I see that my right thumb is pointing into the page, and that is the j hat direction. So k hat cross I hat is actually equal to j hat. Now, the good thing is, in general, when you do this k hat cross I hat cross k hat, I hat cross j hat cross I hat, and so on and so forth, they always come up to plus or minus I hat, or plus or minus j hat, or plus or minus k hat. And of course, if you ever do I hat cross I hat, or j hat cross j hat, or k hat cross k hat, you get zero consistently. So now we have the total answer of this cross product, and the total answer is R dz j hat. So we evidently can suspect that the direction of the magnetic field, which is given by this cross product, is clearly into the page, and that's completely consistent with the right hand rule we already learned about current carrying wires. Specifically, if you take your right thumb and point it in the direction of the current that the wire is carrying, and then you curl your fingers around the wire, then, if you look down from above, you will see that your hand is actually showing your right finger, your fingers of your right hand going in a counterclockwise direction around the wire. Counterclockwise around the wire means that if you're behind the wire, it should be pointing to the left. If you're to the left of the wire, it should be pointing out of the page. If you're in front of the wire, it should be pointing to the right. And if you're to the right of the wire, it should be pointing into the page, which is exactly what we got. So that is completely consistent with our right hand rules. And now we can go about doing the integral. So now I'm going to say B, which is equal to the integral of dB, is equal to mu 0 I over 4 pi. And of course, the mu 0 is just the permeability of a vacuum, which is 4 pi times 10 to the negative 7th Tesla meters per amp. Now I have to take the integral of the dl cross rp minus rdl, which we found was r dz j hat, and then I have to divide that by the cube of rp minus rdl. So rp minus rdl's magnitude is the square root of r squared plus z squared. So I'm going to put r squared plus z squared, and it has to be raised to the 1/2 power because it's a square root, but it also has to be raised to the 3rd power because it's cubed. And I just wrote 3 because I said the word 3 when I was doing it. So it ultimately just becomes that r squared plus z squared to the 3/2 in the denominator. Now, in this case, I can do a little bit of simplification before I do my trig identity, or my trig substitution. I'm going to go ahead and pull out the constants, which technically is r, and really that's all we can do right now, but I can definitely make some use of that r in a little bit. So I'm going to say mu 0 I, and then r over 4 pi. Now, here's the neat thing. Whenever you're integrating or differentiating a vector expression, the I hat, the j hat, and the k hat are truly constant vectors. So you can just pull them in and out of in and out of integrals and derivatives any way you want to. So I'm going to pull the j hat right out in front and just put it in parentheses. And now I'm going to say the integral of dz over r squared plus z squared to the 3/2 power. Now I'm going to do my trig substitution. My trig substitution is going to be let z equal r tangent theta, then dz is going to be equal to r secant squared theta d theta. Not only that, you can create a triangle from that substitution, and you would see that the triangle would have an R here, it would have a Z here, this would be a right angle, and this would be the angle theta, and in fact this would be the square root of Z squared plus R squared. So we can use that, and we can see since our range of integration, our limits of integration should have been from negative infinity, that means z equals negative infinity, all the way up to z being positive infinity, that's equivalent to saying theta goes from negative pi over 2 to positive pi over 2. So I'm also going to say z negative infinity to positive infinity implies theta goes from negative pi over 2 to pi over 2. Now that I have that, I can go ahead and say B is equal to mu 0 I R over 4 pi times j hat. Didn't put parentheses around it this time because that looked kind of cluttery. Integral theta approaches negative pi over 2 to pi over 2 of dz. Now, we already know what dz can be replaced with. It can be replaced with r secant squared theta d theta. So I'm going to say r secant squared theta d theta. And now I'm also going to realize that when I substitute z equals r tangent theta in for z, I'm going to have a common factor of r squared. So I'm going to go ahead and do something with that by factoring it out. And now it's going to be 1 plus tangent squared theta. And all of this in the denominator is raised to the 3/2 power like that. So what we see is an r squared raised to the 3/2, which is going to become r cubed. Notice that r cubed will be in the bottom, and notice there's a new r on top. So we now have r squared on top, r that's next to secant squared, and r that's out in front of the integral. And then we have r cubed on the bottom. So r squared over r cubed just gives us an r in the bottom. That means our result is now mu 0 I over 4 pi r, and then j hat, and then the integral from negative pi over 2 to pi over 2 of secant squared theta d theta over, now 1 plus tangent squared is secant squared according to the identity. So this quantity right here is secant squared theta, but secant squared theta raised to the 3/2 power gives me secant cubed theta. So I got in the bottom here secant cubed theta, not d theta, sorry about that, just secant cubed theta. Now you see secant squared over secant cubed means secant in the bottom, but secant in the bottom is the same thing as cosine in the top. So I get mu 0 I over 4 pi r j hat times the integral of cosine theta d theta from negative pi over 2 to pi over 2. Now, the derivative of sine is cosine, so the integral of cosine is sine. So I'm going to go ahead and write this as mu 0 I over 4 pi r j hat. And then, of course, it's now going to become the sine of pi over 2 minus the sine of negative pi over 2. Now, the sine of pi over 2, of course, is just 1, and the sine of negative pi over 2 is negative 1, and 1 minus negative 1 is 2. So my final answer is actually mu 0 I over 2 pi r j hat, and that is the final answer. Now, it actually helps to think about this. Notice from the symmetry of this wire, it's perfectly round cylinder going along the z-axis, and if I twist either the z-axis or the wire itself by any finite amount, the diagram will look exactly the same. So if I imagine taking the right side of the wire and pulling it around a little bit this way, what I'll see is that j hat vector, which points into the board, is going to continue pointing that way, even though the wire is spinning like this. And that tells me that it's actually consistently pointing in the direction in which theta increases. So a more descriptive uh, uh, direction for it would be that it just points in the theta hat direction. If the current is actually going in the positive z direction, it's going to go in the direction of increasing theta. So for instance, when theta equals 0 degrees, you're actually on the positive z-axis, and it would be parallel to the positive y-axis. If you go 45 degrees from the positive y-axis, then you draw a line straight out from the origin 45 degrees above the positive x-axis, which puts it 45 degrees between the positive x and 45 degrees between the positive y. And then perpendicular to that, pointing towards the y-axis to some extent, is again the direction of the magnetic field. If you go 90 degrees, then it'll be lying right along the y-axis, and this time it'll be perpendicular to the y-axis and pointing in the negative x direction, and so on and so forth. So you see that it actually does behave exactly like the theta hat direction that I've mentioned in some of my other videos. So I hope this helps you better understand how to use the law of Biot-Savart. Remember, the RP is a vector from your origin of your coordinate system to the point P at which we wish to know the magnetic field. The RDL is a vector from your coordinate origin to the DL, which is the vector that points, that is parallel to the wire and points in the direction that the current flows. And that should be able to get you through any type of problem. Now, to be honest with you, we can't do a lot of these problems by hand. Most of them would require some code writing to compute the integral, but this is one of the nice ones. So I hope that helps. Have a good day. Bye bye.